Well, these last three lectures for today, tomorrow, and Wednesday are going to be PowerPoint. And I've got them pre-posted for you, but I may be making some changes or corrections here, so after each class I'll repost the corrected versions for you, or modified versions. What we've done last week is I introduced to you the way we describe systems that are subject to chemical reactions, and then how we can describe equilibrium in systems that are undergoing these processes. And we saw how we could get an equilibrium constant by getting the tabulated standard free energies and heats of formation for various compounds that we can then put together. So I think we're ready to do a more detailed example at this point, and that's what I'm going to start out with today. And the example I want to take a look at here is the equilibrium composition of an ideal gas phase system subject to the reaction where we oxidize sulfur dioxide to sulfur trioxide gas. And we do have some nitrogen present as an inert as well here. So here's the standard way we'll write it out. We write the reaction, then I'm listing the initial inventory here underneath. So I've got a mole each of sulfur dioxide and oxygen, and a mole of the nitrogen. And the temperature is set at 1,000 degrees K, and we'll set the pressure at 2 bar. So our problem is the typical one, and that is to get at this equilibrium composition. So we first want to determine K. Remember, we solve all of these problems in two parts. The first one is that we use the thermodynamics to get the value of K under the appropriate conditions of temperature and pressure. When we've got the value of that equilibrium constant, then we can evaluate it in terms of the activities of the components in the system, and that's where we get the composition. So let's first determine K at 1,000 degrees and 2 atmospheres. And so the starting way that we do that is to get the standard Gibbs free energy change of the reaction at the reference temperature of 298. And remember how we get that? That's composed here as the summation of nu I times these delta G zero of formation for all of the participants in the reaction. So in this case it would be minus the free energy of formation for SO2 plus that of SO3. And for oxygen, since it's already an element in its standard state form, that doesn't contribute anything to it. So we look at the tables that we have for these formation reactions, and I'm just picking out the numbers that were taken out of that table, and we end up with the standard Gibbs free energy change for this reaction at the reference temperature of 298 is minus 70.92 kilojoules per mole. We next would do the same thing to get the standard state free enthalpy of interaction or reaction or heat of reaction, constructed in the same way as we did this. Pulling out the numbers from that same table, we get minus 98.957 kilojoules per mole. And we anticipate the need for this because we're going to have to get a temperature here of 1,000 degrees K, which is different from the reference temperature of 298. So we should be ready to go to put it together. And we had this derived last week. The logarithm of the equilibrium constant at the temperature of interest, I've suggested that with the subscript T here, can be written out this way, provided we assume that the heat of reaction would be taken as effectively a constant with temperature. And if I do that, then the expression for log of K takes the form that I've shown here. And when we put in the appropriate numbers that I had on the previous slide, that works out to this expression. So the log of K is minus 11.3106 plus 11,902.5 over T in degrees K. So the temperature of interest to us is 1,000 degrees. So that'll give us log K of 0.518, or a value of K itself at 1,000 degrees of 1.807. So that's the first half of our solution to the problem. The next is to determine the equilibrium composition from our knowledge now of K. And that means writing out what K is as a product of, this is a gas phase reaction, so we can write it as a product of Ky times K phi, accounting for any non-ideality, times the pressure to an exponent, which is the stoichiometric number for the reaction. And that stoichiometric number nu here is equal to 1 minus 1 minus a half. Remember, our reaction is so you can see what those stoichiometric coefficients are. So the exponent nu here is minus 1/2. Now if we assume an ideal gas situation, which we've been told to do, then we can just set K phi equal to 1, and our expression just reduces to Ky times pressure now to the minus 1/2. So if I put in the numbers for that, then Ky is equal to the K that I got from up here times the pressure with an exponent of 1/2. When I put that in, I get a value for Ky, which is the one I'm interested in now for evaluation of the composition, equal to 2.556. And remember what that is then, is that this combination of the mole fractions in the equilibrium mixture. And it's these quantities that I want to evaluate. Now I do that by relating all of these y's back to the xi, or the extent of reaction. So there's only a single variable here that needs to be obtained. So we express Ky now in terms of xi. And for that, and I think you're familiar with this, we want to set up a standard type of stoichiometric table. And it's good to do this in a routine way. So you write out the reaction here and note the presence of any inerts. And then we have as columns in our table the various species that are involved, including the inerts. And in the last column, put a value for the sum of the moles. And then at first, let's take the initial inventory. So we have 1 mole of SO2, a mole of O2, no SO3 present, a mole of nitrogen. So a grand total initial number of moles equal to 3. Then the y's are formulated in the usual way, here by dividing each of these quantities by the respective total number of moles. And so here are the expressions for the y's, all of the 4 components present. And of course they have to sum to unity. Once we've got that, then I can write the expression for Ky, and there's a typo here. Should be a 1/2 right there, but it was over here, so no problem. It's still going to be correct. So there you have the expression in terms of the x's equal to the equilibrium constant Ky that I evaluated previously, 2.556. So now I need to solve for the root for this expression. And that gives me a value of 0.5676. And I can take that value of xi and go back here and calculate each of the mole fractions, which turn out in this case to be the following. So the problem is therefore solved. Well, we might ask ourselves, are we going to encounter any problems in finding the root that I just wrote it down? And you have various mechanisms for finding it, but it's a rather complex expression, so you could have a thought that perhaps when you just plug in the numbers that you may get more than one root. And there's a way to deal with that, so I might as well say something about it here, and then we'll see it even more important when we get into more complex situations. And that is to, before we even go to find the root, let's find the allowable range for xi. And this is an issue of identifying the limiting reactant or reactants. So in finding the root for xi, it's often useful to first find the allowable range, and generally only a single root will be found in that range. So this is an issue of determining what the limiting reactant is. The maximum value of xi corresponds to the number of moles of limiting reactant present, because the farthest you can go is when you consume all of the limiting reactant. And we identify the limiting reactant as the one which is present in least stoichiometric amount. That is the smallest value of the initial inventory here divided by the absolute value here of its stoichiometric coefficient. Of course, for reactants, nu I is going to be a negative number, so I have to take the absolute value. So we could look back at our situation to see which is the limiting reactant. It's a pretty trivial case here, but I've got a mole of SO2, so I divide by the absolute value of the stoichiometric coefficient, so that's divided by 1. So the stoichiometric amount of SO2 is 1 mole. For oxygen, I've got 1 mole here initially, but stoichiometric coefficient is 1, so its stoichiometric amount is 2 moles. So I see that the limiting reactant, the smaller of the two, is going to be SO2 in this case. So I just have it written out here. And that means that the maximum value that can be achieved, the maximum value of xi that would be allowed to be 1. The minimum value here is 0 in this particular case. But we may have some product present. I mean, in the general case, if I had some SO3 present to begin with, the reverse reaction could run, and that would mean that xi could take on negative values. So we should consider that. If the products were present initially, the reaction could run in reverse, and xi could take on a negative value. Maximum value of which would be dictated by the limiting quote-unquote reactant here for the reverse reaction. Of course, that would be one of the product species. Here it's trivial because we only have one product species. So we will look for, oops. This is, again, it's wonderful software. Even lost my train of thought here. So we could, if we had some SO3 present to begin with, then xi could take on a negative value. But if I set the restrictions like this, before I go looking for a root, you tell it the range in which to find a root, then you're only going to get 1. And there won't be any ambiguity. Well, what about this issue of just assuming that I can take the heat of reaction as constant and therefore get a fairly simple expression for log of the K at the temperature of interest, 1,000 degrees. Well, 1,000 degrees is rather far away from our reference temperature of 298, so maybe we weren't really justified in making that approximation, so we should explore it a little bit further. So for a more accurate determination of log KT, we go back to the original expression, and here there should be a dt there, of course. But it means integrating this expression now where we allow the heat of reaction to actually be a function of temperature. And I can write that out as what the heat of reaction is at the reference temperature of 298 plus the integral of its temperature derivative here from 298 up to the temperature of interest. So what I would need to do then is plug that expression in here. But I need to concern myself now with what this is. So if we recall that the heat capacity here at constant pressure is defined here as the enthalpy derivative with respect to temperature at constant pressure, then I can write the expression here. We're all at constant pressure here, so I'm writing it as a total derivative. It's just equal to this delta heat capacity, but that is for any property change of reaction. It's written out this way. We've seen that over and over again. But now what this refers to are the stoichiometric coefficients of all of the participants in the reaction here times their respective heat capacities. So this is the thing here, we got that will go up in here. Now we can write this expression out in terms of the expression for the temperature dependence of the heat capacities of all of the individual participants in the reaction. And we have those tabulated in the appendix of your textbook in the following way. The heat capacity here is the gas constant here times function of temperature, which is some constant plus another constant times temperature plus 1 times t squared, then another one over t squared plus possibly t cubed. And we've got these tabulated for quite a large range of different substances. And so we will pick out the ones of interest to us as oxygen, SO2, and SO3. And so here we see we don't have a value of C or E, so we're lucky that way. So it makes our computations a little bit simpler, but we have the values for A, B, and D. So we should be able to evaluate this. So if I write it out, then delta CP looks like this, where we now remember these deltas, delta A, delta B, and so on, are all calculated in the same way. These are like property changes of reaction constructed by that same formula. Now we put all of this together and it looks fairly hideous. But this is the expression that we get when we carefully put all of this together into the integral. So it's tedious, but nothing difficult. This is my log, we should recognize this is log k of 298, this first expression. And here, let's note that these brackets are fairly big, so should have been able to write them like that. But we should be able to, for any case that we might encounter, now get log of kt in terms of this log of k at 298 plus this whole expression. Yeah?
Does that equation only apply to gases, or can it apply to solids and liquids?
Well, it could apply to solids and liquids as well. But I think that's in the heat capacity information is in a separate table. But they exist as well. Yeah. Anything else before I go forward on this? And you do have one homework problem which does involve a solid. And you're given information for that, so you could go and just evaluate this. In our case, here's what all the numbers break down to. So delta A takes on this value, delta B this, delta C and delta E, of course, are 0 because C and E values for all of the compounds were 0. Delta D takes on this value. We've already calculated these guys in the previous computation. So this now, when we put all of this together in accord with this formula, what that finally gives us is this. So now we've got log of k at the temperature of interest, is a little more complicated function. And here are all the numbers. Before we just had a constant plus another something over the absolute temperature, and here we got some other terms involved. So the question is, how different is this going to be? This gives us an equilibrium constant at 1,000 degrees of 1.8560, and we compare that with the number we got before, 1.8070. So it is different, but not a lot, not by a lot. The equilibrium xi value, 0.5742, compares with 0.5676, so again, a little bit different. And the ultimate, what we'd be most interested in here would be the mole fraction of our product, SO3, which is 0.212, and that compares 0.209, what we got if we assume constancy of delta H. So how do we come out on that? If I plot it up, here's a plot of log k against 1 over t in the range that we're interested in. Here's 1,000 degrees right here. But you can see I've just plotted it between 900 and 1100. And by the time we get to a little bit less than 900, it's less than a line width apart. So really close. And you can barely see it, the difference here. When you get up to still higher temperatures, then the difference will start to diverge and it will become more and more important, as you would expect. So this gives us a good idea of how important it is to account for these temperature changes. The take-home is that for small molecule reactions, you can usually get away with quite a bit by assuming just constant delta H.
Are your temperatures backwards?
Excuse me?
it's not really important, but are your temperatures on the x-axis backwards? It says 0.00110 below 900 K. It says
Yeah, the temperatures run backwards because I'm plotting it here against 1 over T. Okay?
Well, wouldn't 1 over 900 still be on the left side? Because it's 0.00.
Actually not. The smaller the 1 over T gets, the bigger T gets.
Okay, I see.
So this is okay. So summary for a given idea, here I kind of want to make a point. What we've obtained ultimately when I put all of the information together is a relationship between the variables, which are the temperature, the pressure, the initial inventory, and the composition as given by Xi. So we've got 4 variables and a relationship that relates all 4 of them. And any one of these can be an unknown. What I've done is take the traditional approach of saying we're given the temperature, pressure, and initial composition, determine the equilibrium composition. But I could have been given, let's say, the pressure, the initial inventory, and a composition and said what temperature is going to be required to get that composition. Or what pressure might be required when the others are specified. So here's the general equation, but it's got a couple of bad typos in it. This, of course, should be no subscript at all, and this should be new I up here. But this is that general relationship that relates all 4 of these variables to one another, any one of which could be an unknown. All right, let's consider here what it might look like if we have something other than an ideal gas. So for non-ideal gas systems, this KT, of course, KT is obtained in the same way. That's just a thermodynamic thing based on standard states. So we're looking at K as expressed in terms of activities. There's where the effects of non-ideality come in. So we're looking at what I'm calling the stoichiometric evaluation of K. That is K here as product of these activities. That's what I'm talking about. So it can be decomposed into product of 3 things, the Ky for non-ideal gas systems. So Ky times K phi times the pressure raised to an exponent, which is the stoichiometric number for the reaction. And this is a reminder, because this right away looks strange because K expressed in terms of activities, and when there is no subscript, then that's the assumption. It's in terms of activities, must be dimensionless, because of course all the activities themselves are dimensionless. But here it looks like I've got pressure involved, but that's really a disguise, because what should be here is P over P0. The new, and P0, remember, I've set as a standard state pressure is set as 1 bar. And that means that P itself must be expressed in bars. That's an important point. So this is, in fact, dimensionless. We haven't really changed anything. So the problem that we've got here is this guy, if I have non-ideal gases. That was just equal to 1 if they were ideal gases, because all the fugacity coefficients themselves would just be those corresponding to ideal gases. So let's note what we've got here. K phi is evaluated in terms of the individual component phi values, but these depend on the composition, on the y's, and we don't know them going in. So problems of this type are solved by iteration. So that iteration requires that we get started with some value of these y's so that we can calculate the phis and therefore K phi. So we start by just setting K phi equal to 1, and that'll give us a provisional set of y values from which I can calculate a new K phi and then iterate that guy to convergence. So I calculate phi values for all of the I get an initial set of y values and then calculate all of the unbelievable. calculate the initial y's, assuming ideal gas behavior. Then I've got the y's, so I can calculate all of the phi values, and hence k phi, then get a new set of y's, calculate a new key phi, and iterate that convergence. And almost always that converges very quickly, so you wouldn't need to do it more than a couple times to get it to converge. Problem is that evaluating these phi values can be quite tedious. So let's look at that. Calculating these phi values for the components in this reacting gas mixture, probably the easiest that we've got is if we assume the validity of the Pitzer equation for describing the volumetric behavior of these mixtures. We've worked it out for that case. But you should realize that this is just probably the simplest case. There could be other equations of state that could be implemented as well. But generally, when you're dealing with mixtures, virial expansion-based equations are the best. So if we assume that we've got a Pitzer gas, then for a binary, these expressions are in your notes. I've got log of phi1, log of phi2 expressed this way in terms of the virial coefficients, and they involve the cross-virial coefficient here in these expressions for delta, if you remember those guys. And these are what the deltas are. So this is pretty straightforward if we have knowledge of the virial coefficients, including the cross-virial coefficients. But there are very few reactions that end up just as binary mixtures. And that's as far as we went in this derivation, but the general expression to the log of phi in a system of any number of components is the one I've given here, and we can take a look at it for a second just to see what it is. So here, the log of the free acid coefficient for component I, P over RT, here's the coefficient for I itself, then plus 1/2 this double summation, and that involves different deltas here. So here I've got 2 delta ij minus delta jk. And if you take the trouble to write that out, even for something as simple as a ternary, it's pretty tedious. And if you get more components than that, then even worse. Of course, you could set it up on a computer spreadsheet and then it would be okay, but that would be pretty tedious to even set it up. So this is just as a preface to motivating us to see if we can get away with the Lewis and Randolph rule, which makes things tremendously simpler. Because remember, the Lewis and Randolph rule tells us that it's only pure component things that matter. And in fact, the consequence of the Lewis and Randolph rule for fugacity coefficients is that the fugacity coefficient of a component in a mixture is just equal to its value as a pure component at the same temperature and pressure. And these are pretty easy to get at. So remember here, log of phi, if that's just a pure component, is just the virial coefficient times P over RT. So if I put that together to get the log of my K phi value here, it's just going to be this, which is a summation of quantities, all of which pertain to the pure components and are independent of composition. So you could calculate it once and for all, so that K phi itself just takes on this very simple expression. And that's what we get if we are going to use the Pitzer type equation of state as our means of evaluation. Now, of course, I could use other means for getting these. And another handy way that we have is to use the Lee and Kessler tables, because now we're dealing with pure components, and so it's valid to use those tables under those circumstances. So that's how we handle that. Another important case is for reactions involving gases and pure solids or liquids, and there are a lot of examples of these kinds of things, one of which is in your homework. So some examples are the oxidation of solid carbon to form carbon monoxide. So we've got a solid reacting with a gas to form a gas. You heat up calcium carbonate, the second example is solid. You'll drive off CO2, so that produces quicklime, calcium oxide, solid plus CO2 gas. If you heat up ammonium chloride to a high enough temperature, it'll decompose into ammonia and hydrogen chloride, so a solid goes to two different gases. If you react a gaseous H2S with gaseous SO2, you'll get a precipitation of solid sulfur, and then either water vapor or water as a liquid, depending on what the conditions are. And many other examples could be given here. So this is an important type of reaction that we might need to consider. So let's see how we would analyze that. Here's the important thing, that recalling that for moderate pressures, that is things under about 20 bars, the activities of pure solids or liquids can be just taken as equal to 1. And if we take that, let's assume that that's going to be the case, then K can be decomposed considering only the gas phase components. So we've got KY, so I've got reactants that are gases, reactants are products that are gases, and they're all that's involved here. The solids don't enter. And the K phi also is going to involve just the gas phase components. And here's probably the most important one. This is phi is just for the gas phase components. In other words, you can reckon the stoichiometric number using just the gas phase components. So let's look at an example just to illustrate it. You take this first reaction, the oxidation of solid carbon to get carbon monoxide gas. Then K would be here, just in general, I can write it out in terms of these activities. So it's the activity of CO in the gas mixture over the activity of carbon, that's a solid, so there's no hat over it, just a pure solid, times the activity of oxygen with this exponent of 1/2 here as indicated. But now remember, we said that this is just going to be equal to 1 at all but high pressure situations. And there's the K phi that's involved doesn't involve that solid component, so these are just the gas phase components. And now P is going to involve just the gas phase components. So the relevant value of nu up here for the gas phase is just going to be 1 minus 1/2, or 1/2. So everyone get that? So continuing here, then I have a KY written just for the gas phase, that would be this thing. And if I assume ideal gas, that's just going to be equal to 1, but I could work it out if it were something other than ideal gas, and just involving the relevant phi components. So my final expression looks like this for K. And then I can proceed from there, as I have in the previous cases, to analyze for the equilibrium gas phase composition, for example. However, reactions in solution, which means in liquids. Well, I could write out the equilibrium constant as always as this continued product of the activities raised to their stoichiometric coefficient powers, but now the activities take